Yeah. So, hello everybody. Thank you for joining the next episode of the podcast, which is TMM Season 0, Episode 2. And with me, I have the almighty Matthew and a new friend called James from Austin, Texas. Hello, James.
How you doing?
Doing good. So, Matthew, James is your friend. Do the introduction. Tell us who he is. Like, what's happening?
Thanks. Well, hi, Matthew Smith here. So I'm in Grenoble, Southeast France. And James, we met over LinkedIn.
That's correct.
And
we had similar backgrounds. We knew lots of people from Schlumberger from work inside Houston,
Yep.
Oil fields and everything else like that. So lots of mutual connections, like Mario Schiak, who has been there forever. As I think CISO emeritus, may not be that way anymore.
Yep.
Big investor in the cybersecurity community in Houston. And I think you've even been to HughesEcon and some of the other ones that are actually like very operational technology focused,
Yep.
Automation focused. Maybe we could just start calling it that. So, and critical infrastructure, because Houston's kind of the core of that in the south of America. In the southern region, there's no bigger critical infrastructure location. And that even means for DER now, too. Greentown Labs has a very, very big office and installation here where a lot of the distributed energy resources startups are beginning, actually. And Matt and I have a whole big lot of time for DER, specifically around the work he does.
So what's DER?
That's a great question. Distributed energy resources, right? Battery technology, but more to the point, renewables, anything that's not very large infrastructure based, right? So we're not talking about large transport like pipelines. Actually, I take it back. Smaller pipelines and umbilical could probably be considered that too, depending on how it gets utilized. So there is some midstream that falls into DER as well. But DER is really just not the gigantic generation facilities, whether that be nuclear, steam driven of sort, that sort of thing. So that's really DER falls, everything that's not that falls into the DER territory. And really what is it about is, especially in the Gulf Coast where I'm at, because we have a lot of natural disasters, unfortunately, specifically hurricanes and flooding, is really to make the grid and our lives a little bit more resilient, to make what we call Western society a little bit more resilient. And that's really where DER is actually helping a lot right now today. So, regardless of how those things are being caused, don't want to get in the political situations, better stay away. So
you both basically you work both in a similar field, meaning like Matthew is doing embedded devices for energy companies and other, of course, and you work with energy companies.
I've worked with them. I do cybersecurity for them. But more to the point, I actually have my own startup too, which is a thin HMI, specifically aimed directly at initially electrical co-ops, because in the United States, electrical is handled very differently than a lot of other places, specifically Texas, where it is very unregulated compared to most places. And these electrical co-ops are smaller communities, usually around farming, which, again, Matthew has a whole lot of time for as well. Those communities usually have automation systems and critical systems that are actually sometimes as old as Windows Vista. I've seen a dam run on that before, or even sometimes Windows XP embedded or something along those lines. I've seen that as well. So, and that's one of my aims, is to make something that's open. I wouldn't say inexpensive. That's not the way to put it, or cheap or any of those sorts of things. But basically,
efficient.
There you go. Efficient.
Capital efficient. Yeah.
There you go. Well, not capitally intensive up front. That's probably the best way to put it. So, places
but
where
so are you talking about a device or the operating system or a platform?
All the things.
Hmm.
So Matthew actually has really nice hardware, which is one of the things that we've been looking into using over here in the U.S.
Mm.
Some of our projects. But more to the point, the hardware has to be one of those things where it has to be fit to the purpose, right? And that's one of the biggest problems that you have in automation and critical, some of the automation systems and stuff like that, is that they kind of use a one size fits all approach. If it comes to wastewater, if it comes to electricity, or lots of things like that, some of the different manufacturers actually have the same exact gear for one to the other, and they're saying, okay, even though that you're, this is just a wastewater thing, it's a very small facility. We want you buying this switch, which costs $8,000 or $9,000, and we want you to buy, our firewall, and we want you to buy, this particular software package that nobody knows how to operate.
Mm-hmm.
And then we're going to put it all together in something called a skiff, right? Which is sort of a total black box package for you. And then you're going to either have to train people how to operate it.
Mm-hmm.
And then anytime you need upgrades or anything else like that, you have to come back to us for that sort of maintenance and,
So
and the
that's
system upgrade.
what's then causing companies to never upgrade, to never do any patches, etc., because it costs just too much to do, right?
Yeah.
Now you get it. So,
Mm.
and it's not that those automation companies, the big ones, the big vendors, are meaning to do that. It's their upgrade cycle is very slow as well because of just market forces, right? How much money that these places can spend, how large they are, and unnimble. And that's one of the biggest problems in the automation world, is that it is not nimble. And I think Matthew and I are trying to bring a little bit of that nimbleness, that flexibility, from the world that maybe now people consider IoT into the OT world, but continuously make it more, maybe even more resilient, maybe even more hardened than the systems that are already in place. Because lots of people say, "Oh, well, this is hardened; it's resilient. We architected it correctly," and then of course we end up with the shenanigans we currently have with pipelines shutting down and communities having water filtration issues and
Right.
anything that winds up in the news. So.
May I add a little compliment to what you just said, James? Thank you very much for what you just mentioned. So one of the other issues that we have, which I think is actually spans industry sectors, is that automation infrastructure and automation systems, the capital expenditure or the investment is very often aligned or bundled or folded in to the total capital works budget for machinery and assets, right? And we know that when we're constructing a building, a factory, an assembly line, a waterworks, a power station, right? A boiler, for example, or a rig, or a platform, you've got certain elements that have a very long lifespan. And so there's this expectation that everything is kind of folded into the same amortization plan, right? So for depreciating that asset. And it's very common to, again, find systems that were, again, installed 15 years ago and they're still running because, well, it was part of the asset. And so it was accounted for as part of the capital works.
Bundled. That's
so
the thing.
Exactly. And that's where you end up with this, mismatch in life cycles. All right. And because integrated packages or integrated systems for automation, tend to get delivered as a one-shot, turn the key and it works, and it's been
there's a reason behind that, though, right?
Yeah.
Lean manufacturing, which is the backbone of modern manufacturing. It's really it started with the Ford process, and then Kaizen came in with Toyota-san, brought in Kaizen across the planet. You had the experiments in the U.S. and California initially, and then it became this is the reason why we ended up with kind of a globalist thing whenever it came to manufacturing, is because there's these centers of excellence where we did something very, very well, like machine stamping, or So one place would have the water mold, new water molding, and one place would be very, very good because it would either be close to a supply line, the electricity or energy would be cheap, labor would be inexpensive. So there's the reasons why they have these centers of excellence, especially in manufacturing. It's the reason why globalization has done so much for the global economy, is because of those centers of excellence. Well, Matthew just pointed out, when that stuff gets deployed, it's deployed as a monolithic package and it never changes. And lean manufacturing speaks to that whole idea of, I want to do it this one thing in Baytown, right, Texas, but then now I want to take that same exact process and put it in Germany, right, or in Africa, or in South America, right? I'm going to literally cut and paste the code, the networking information, even sometimes this thing called a media access control address, which is basically the hardware address of the machine itself. And I'm going to cut and paste all that logic from one to the other, because my whole idea is I want to cut out any mistakes I make on a process over and over and over again. So if I do something and I make these incremental small changes to always make the process better, to always cut out errors, I don't want to take all that human investment, the human capital that I put into something, and waste it by not reutilizing it, right? So I've cut and pasted the exact logic from one to the other, and that's the lean concept. That's this Kaizen piece. And so that's the backbone of modern manufacturing. It's a waterfall-like process. And we already know from the IT world that worked at one point in time, but it led to these massive lengths of these projects, right? And because of that, it kind of set them in stone, almost like put them in carbonite. You're frozen in place, and that creates a bunch of big problems over, because you keep piling up technical debt over a very long period of time as that goes along, right? And so they don't do that in IT anymore, in the IT world anymore. OT stuck back in the lean manufacturing world. Not much has changed there because people are kind of afraid to start changing that or taking some of the risks. It's out of bounds for a lot of risk managers because they don't monetize or capitalize that technical debt. It's missing.
And how? So your approach would be to create a custom solution for each environment.
Well, not custom. Custom's tough, right?
Right.
We're trying to open the system. So lots of people say, there's these new, and I hate to say it, competing solutions to mine and even sometimes Matthew's. Induction automation is doing a lot in this field, right? Where they're trying to open it up. And so they're using these more open protocols so people can extend those protocols themselves, right? They can take it and extend on the protocol itself. And that's MQTT, formerly Mosquito, and now Sparkplug, I guess, is the newest version that everybody's starting to use. But this idea behind MQTT is a protocol for data acquisition and some supervisory control, some, not a lot of it, but some control. So this idea is, but behind induction and a couple of the other, newer control and automation companies, is they are now trying to make protocols that are more extensible. So you may not change the whole process, but you can add bits and bytes onto it. I think at least I am trying to overlay what is already there, and then go even a little bit faster, where you can do dynamic packages and take your digital twin directly from, wherever you're using that logic or that digital twin, and then be able to float it down into your architecture. And if, say, you have a plant turnaround, be able to collaboratively test that thing right then and there. So that actually almost makes the whole process agile. I'm trying to take us into an agile world from
right.
water.
So how do you plan to make sure that the code, like for example, there is a new patch, security patch, right? How are you ensuring that it goes through the right tests?
That's a great question. So I mentioned digital twin already. The idea is not to have a full perfect digital twin of something, is to have a digital image, or I call them replicas, right, of what you've got. It's very hard to actually have an exact replica if you just have hardware emulation, because there's so much on the physical side that you cannot emulate. And actually, one of the things that Matthew knows, the reason why you said bespoke earlier, custom, is because that pump maybe we call them VFDs, or it's a variable motor, right? Like that pump that's actually in a plant, it may operate differently in Baytown, Texas than it does in Germany.
How come?
It's hotter there.
Okay.
It's way more moist here. God, I live in a swamp. Like, literally, all the Gulf Coast of Texas is basically all swampland. So there's just a whole bunch of variables. I mean, heck, maybe even, galactic rays are different in Texas than they are in Germany. Who knows, right? So they just operate differently from each other. So when you do what they call an FTA, which is basically an acceptance test of this piece of automation gear, whether it be a pump for wastewater or electrical controls for breaker switches that help give electricity to your house to operate the cool lights that you've got going on behind you, right? So those are different from one location to the other because physics are different in one location as opposed to the other. Like I said, there could be a billion variables to make them a little bit different. So you have to acceptance test. So that means there's a little bit of tweaking on the back end of this to get things perfect always with everything, right? So that's one of the reasons why the cut and paste stuff doesn't always really work. So a lot of engineers will laugh at it and say, oh, you did this, but you can't just cut and paste. You have to go and test, right? So the idea is to try to make the digital twin that you have as close to reality as possible, change as many variables as you possibly can, and then take what you did there and float it down and actually test for real. So what you're going to have to do is flop out that logic. But right now, PLC code, programmable logic controllers, to flip them out, you actually have to reprogram the whole thing, change all the ladder logic, and then turn off everything to do the thing, to get the thing going, right? And then you may or may not have problems with the PLC because it may not have the same firmware that does all the brand new logic you want to be able to do. So there's like all these little variables to update that PLC. What if I could actually take what the IT world does, specifically around the cloud, Netflix or Facebook, or you name whatever cloud social service or service you actually have, they use containerization, basically like to be able to flip out these things. And Netflix specifically called it chaos engineering, right? Where I can actually take something, flip it in, flip it out very, very quickly, and then know that if it did not work, I'll be able to acceptance test that thing within seconds because I've got my nice little scripts I run against it. Oh, it works. Great. Let's leave it in. Now we can actually go, do the actual real test and then put it directly into production. Wait, it doesn't work. Great. Flop it back out again. We're done. You cannot do that with a PLC. You can't do that, with a lot of different things. So the idea is to try to make it not chaos resilient in that way or chaos engineered in that way all the time, but be able to take this idea of a digital twin and actually make it actionable, right? Like real-time action. I float it in and change it real time. If it doesn't work, then flop it out, that sort of thing. And so that takes us into a lot more agile world by just using a different way of doing application delivery, because we've been stuck in the Win32, Win64 application delivery world. Hell, even Linux, LAMP stack, application delivery world forever. The cloud has moved on. Mobile devices have moved on. The application delivery stack for this is generations different from what we currently still have in automation, right? And there is no user space in this. The users, you're not the administrator of this thing, really, not at all. Your telephone company is. There's a whole management plane. You don't have access to this unless you hook up a special serial port to it and hack the operating system and remove all the security bits and everything else, and then you can get to the user space on this. But that's not the norm. That's one of the reasons why these people call them walled gardens. They're not completely walled. You can break through that wall pretty easily because you have physical access to the device. So, but that's not the norm, and that's the reason why these aren't as much of a security problem as my laptop. Now, I could hold up real quick, but I won't because I'll probably disconnect a whole bunch of
think people know how a laptop looks.
Yeah. So that's user space. And we have this idea in critical infrastructure, still using user space in critical infrastructure.
One question, like to make it clear, what do you mean by user space?
So your Windows, Linux operating system, Mac OS, right? When you're in user space, you have complete autonomy, especially if you have administrative access to the machine. That is the space that you are in, and you can then modify almost anything about that operating system. You can update things, you can build things, and all kinds of stuff.
So basically,
You can't do
I logged in using a system with admin access.
Yeah. I can do whatever I want to that system, or maybe systems it's connected to, but I can't do that with this, right? I can create content with this, which is what we need most users to do, right? But we don't need that. So this is a management plane. The user space in this doesn't really exist, right? The content is somewhere else doing I just create content with it.
Right.
The user space that I have, on those other machines is a completely different, territory. So we've got to basically take user space, which is, I get to use this operating system. I get to do all kinds of really cool things with it. We got to take that idea completely out of it.
Yeah.
So when it comes to those, Matthew, do you want to say something?
No, I just wanted to add that on the, if we take Android as an operating system, okay, and so Android has a kernel, right, a Linux kernel. So your phone, right, actually boots a Linux kernel if you have an Android phone, right? And normally the Linux kernel, right, again exposes the kernel API to the user space. Okay, and that's how, normally on a regular Linux system, you end up with basically a whole sort of process management piece. So there's the init system, or the system daemon, that basically is executed when the kernel fires up. And that basically allows you to then, again, have some user applications. And that's the user space that interfaces with the kernel APIs. All right. But under Android, it's rather different. You don't actually have a shell, and you don't have an init system. You don't have a system D, all right? But you have some hooks. So there's a very specific and a very different type of user space that is exposed into this whole application environment. And as a user in Android, you basically are literally interacting with applications and never directly with the operating system. Unless you go low level. Did I explain that well?
You did great. And I would add that I had a professor that said something that I will never forget, and it was one of those light bulb on moments for me. You can solve any problem in the world with one more layer of abstraction.
Yeah.
Yes. And that's basically what has happened, right? This new application paradigm that we have is a whole other layer of abstraction, where we've now abstracted completely away from kernel space, people having direct access to the user space being directly next to the kernel space. There's this whole, and I have a presentation that I gave at s0e2, which is a cybersecurity conference. A lot of it focused on OT. Not even a week or so ago, I was actually out there, and that's part of what I say is we've got to get rid of some of this stuff. I think I was also on GrimCon. Grim has a cybersecurity conference. I don't know if you've heard of Grim, with their cybersecurity company, GRIMM. And they are about IoT hacking. That the Grim originally started as a company that would go and hack IoT stuff specifically for people, and that was one of the things, that if you had kernel space too easily accessible in your IoT gear, they were able to always pop the box, so to speak, right? So that was part of my speech as well. Is we just got to keep, we got to abstract things way better than we're currently doing, and actually have a different paradigm of application delivery, specifically in critical infrastructure, but more so just across the board. Don't get me wrong. You're going to take my Windows or Linux machine away from me, from my cold, dead hands, right? You'll never be able to take it away from me. But I'm a programmer and a user, or not a user. I'm a programmer and a builder. I do things with that space, right? Most people don't need access. They need to content create with it. That's it.
Right.
And interact with content. And that's the reason why they don't need access to that space anymore. Just like they did with back in the day when they had when Microsoft originally started creating that kernel space, and then Unix was always there, had that kernel space, and users were simply protected memory was protected memory, right? That's where all the kernel operated and drivers and stuff like that will go back up to the MS-DOS days. I could go use the debug thing in Windows and actually directly do stuff directly to the hardware. Well, you can't do that in modern Windows operating systems. They've abstracted again. We're at the level where it needs to be abstracted again, where we need that extra level of abstraction because unfortunately we've got a situation now specifically around not just cybersecurity, but just operation of some of this stuff in general that we just have to go and do that abstraction again and put everything behind an API now where we can actually then control the API and then, okay, now I'm going to build all my applications on top of APIs. Fantastic.
So you guys want to build something like that, like a solution like that, a platform that you have just API?
I've already got one.
Okay.
I've already got a thin HMI that can actually do some control, supervisory control, that I actually put everything into an API. I take Modbus or some other OT protocol that's all serial based, and I put it directly into a real-time API. And then I build applications like HMI on top of human machine interfaces or SCADA or data measurement or something else like that. So everything's an API after that. So you take it as quickly as you can and take it, put it directly into an API. That's your data layer. You can do whatever the hell you want to with the data layer. After that, you can subscribe to it, publish from it. You can build on top of it, anything you want to.
So basically, then the idea is that using this approach, anybody reading the documentation can say like, I want to attach mouse to this thing, how I read the data, how I send the data back, and they don't need to know like how the hardware works, how to talk with the kernel, how to talk with the hardware. It's just, this is a standardized way to interact with these type of devices.
There's no patching to it. If I want to upgrade something, I just swap it in and swap it out because it's behind a whole load balance layer where all I do is API, just like I interact with Facebook or Netflix.
Yeah. Right. So they change the background, you know, the database from Oracle to MySQL to Postgres to whatever, and you don't know, have no clue because you're just using the website and it still works, right?
Nor do they give a crap. Yes,
right,
exactly.
Although you're like a developer making a game on Facebook and everything still works, right? You're just using API. So, okay, that's interesting. Yeah, because without that approach, if you're, especially you have to do something with Linux, yeah, you just have to know how to build your drivers, how to interact with the kernel. You have to know all of that stuff, and either you know how to do it well, or you just hack something together. Then someone else says like, "Oh, I can flip a bit, and now I'm an admin," right?
I'll do you even better. I've even flopped out my delivery platform completely. I was using K3OS, which is a Kubernetes cluster, and then I put in a Zadita, and then I put in the load balance cluster as part of just a member that I could then load balance over to, and then I swapped out the entire application delivery platform directly underneath it without losing any data whatsoever.
So wait, so you have a bunch of containers.
Yep.
Okay. So I as an external person have access to the API container, I guess, right? That sits at the top.
Yep.
And then there's another layer that there's another container that you do all your magic. No, sorry, there's the load balancer, right?
Well, there's two different database layers. There's a sandwich of databases. One's a real time. So I take we'll call it a Modbus worker, right? And so I'm listening on the wire for Modbus commands and sending directly on the wire from that. And that requires a special, if you know anything about Docker containers or any kind of containerization like KVM, you know that you have to have kind of a little router that it all goes through that actually interacts with the kernel level on the wire, right? That little router is untouchable. So the Modbus worker reaches out to that, subscribes to a piece, takes the Modbus data directly into the container, makes sense of it, drops it directly to the adding its tags and all the kind of stuff like that, drops it to the Redis database with all its embellished information about exactly how it's going to get loaded and stored. That gets then copied directly into the MongoDB layer. From Mongo, you publish directly to an API, right? So it's actually way more intrinsic than that. There's a lot more to it.
So you're using databases to move data in and out.
Two different types of databases to move data to publish to move data in and out. Yeah, and it sounds really heavy, but it's not. We can do it all on a Raspberry Pi.
Nice. Okay, so interesting. So that's why so how is it that you can swap? So when you said like I can swap something and you don't lose any data, are you talking about the layer before the databases? I'm assuming, right?
Well, do you remember there's the least principal when you're talking about security design, you're talking about least principle design, right?
Hmm.
When you're talking about resiliency or availability design, you talk about you have one thing that does this thing very, very well, right?
Hmm.
So every container I have is the container that does that thing very well. We have a container that is specifically to a certain type of DB. We have another container that's specific to another type of DB, right? Those are completely separate containers. So if I decide I don't like Mongo anymore, I want to use, something, like bigger and more scalable, I can then flop the Mongo out, but I still have my real-time database there. It's still there, right?
Mm.
And that actually has hooks that are, to that container that go directly to permanent data storage. So it doesn't matter what I have there because the container is immutable. It doesn't really change. It's just presenting the data through it. The data underneath you still can't get to anymore, which is the beauty and what we're talking about, that abstraction away from the user again of access to that data. Whereas if I have a Windows machine and I've got a database server running that, I can go directly to the data exactly where it's mounted and start playing with it.
Right. So,
as a data as well. This the way I got no access.
right. So how is it that you don't have any access? I mean, if I have access to the Raspberry Pi, I have access to the whole operating system.
Okay, physical access, you cannot solve that. I'm not trying to solve physical access issues. I'm trying to solve if I have logical access over the wire somehow to this thing, even if I have access to the outside of this container or directly to the API, there's nothing underneath because the API is being presented directly through a security proxy that actually can run security through it. So I actually, the first thing I'm touching when I'm touching the platform is actually the security device.
Okay.
After that, or can't get through because I've done something stupid. Now that doesn't stop me from misconfiguration. I can certainly misconfigure something and things like that. It's certainly that sort of thing. But more to the point, that's the reason why you go with a platform provider like me, because I've already done this. I've already hammered it out. I've already pen tested it. I've already done all the things, as opposed to saying, "Oh, I'm just going to go build it myself."
Right.
I like his plan. I'm going to go do it myself. Well, then all of a sudden you can end up with this big misconfiguration, and you haven't done acceptance testing and all the things that I've actually spent the technical debt to do, which is the reason why you should go with me and not try to roll your own. Because I'm all for the roll your own thing. I want to make sure things are open.
Right, but I'm just trying to understand. So when you have the device, let's talk about the Raspberry Pi, right? And you have all the custom software, like custom solution that you wrote, right, which is the software. I get a username and password to access something, or you're exposing some just general API. Well, no. Okay, so I have this Raspberry Pi. I have to somehow be able to log into it as a user, correct?
That's right.
And then there's like a daemon running with your API stuff, kind of.
Right. Well, okay. So getting away from the actual physical hardware, right? The way that you get to my system is actually if I walk up with a tablet that has Wi-Fi access, or maybe I'm using a software-defined radio that has a license band on it or something like that. That thing, I walk up and I get onto the platform from there. So like I pull it up and it's a web browser, right?
Okay.
So there's no direct access. We're not logging directly into the Raspberry Pi at all. The Raspberry Pi is just allowing us to actually have an IP interface to it, usually over some web browser. So that's becomes the web browser becomes my HMI. That's what it is. And actually, you're going to laugh, but most HMIs are actually already done that way. So most HMIs are actually embedded Windows 10. If you're using, I don't mean to call it manufacturers, but they're just a good example because they make a good HMI, is Red Lion, right? Is very, very often used in a lot of stuff. Well, they're using Windows embedded. Well, sometimes it's a little bitty executable running on the Red Lion. Sometimes it's just a web browser that they pop up and it just kind of comes on. And it's got a Red Lion interface and you get some sort of IP interface to it. Sometimes it's some sort of serial application, depending on how and what you've done to program that HMI. But it is just a Windows computer, right? Popping a Windows computer as opposed to something that's not even running a GUI, right? Because that thing actually has a GUI in the background. Something that's not even running a GUI, your GUI is then abstracted onto whatever tablet or BYOD, or maybe down to the tablet you're going to use. It's two completely different spaces, right?
Okay.
You no longer have user space on that HMI.
Right.
It's completely
and so
separate.
as from a developer perspective, let's say I have the device in my system and it's monitoring, I don't know, pressure sensors, right?
Right.
And so I can have my tablet connect to the device over a network and see like all my pressure sensors that I have in my whatever.
Right. Hmm.
And now I want to send this data to Datadog,
Yep.
and you don't have this feature built in. What do I
Sure I
do?
do.
Well, but let's assume
Uh,
you don't, right? Let's
okay.
assume
I don't.
there's a missing feature that I want to have in my solution. So what do I
Sure.
do? Like I go to you and say like, hey, can you make me this? Let's call it plugin, module, whatever. Or can I go to you go to Upwork and say like, hey, developer, I need this to be sent somewhere else. Can you do it? How does it? How
So
does it
if
work?
you're, let's just say you got Modbus and your pressure sensors are sending, Modbus across a wire, right?
Mm-hmm.
So that floats into the Redis database. One of the things that we've got is we've got a little bitty engineer interface that says this is the data I'm getting, this is the tags on it I'm getting, and these are the endpoints I'm actually getting it from. So you know the serial address of your IED, which is your sensor. Your IEDs are intelligent electronic devices.
Okay.
You can actually then take that, tag your data onto it. That floats directly into my RESTful API. So it goes directly into REST. You pull up the REST API, it comes up and says, this is your site, and these are all the different REST endpoints that I've actually got. I can then go to that REST endpoint, grab the data just with a simple old get, HTTPS
Okay, so
get.
I can have my own internal on site little other Raspberry Pi or whatever computer and write my own custom code that every minute picks the data from there.
That's right. You don't even need my HMI to do it because it's already in the API. It's just whatever goes to a Modbus, I can put directly into the API real time.
Right. So
And you can data map it. And as soon as you data mapped it and added your tags, it goes directly into the REST. And then you can take the REST and then you know exactly what tag types they are, what data types you're getting out of it, whether it be a bool character or a hex character or hex information, or if it's a character itself. You even get that data out of it, what you can actually query for, because that's one of the biggest problems when you're dealing with programming is what data types am I getting from that endpoint? Where, what am I going on? Well, if you have it available and exactly what's coming out of it, that's even way more valuable because then you can do all kinds of crazy stuff with the code directly on site. I want to take that data. Now I want to take, what's coming in from those pressure sensors, and I want to take that into another program, into my custom made DCS, or maybe I'm, taking something out from a DCS or a little program I create, and then I can actually create that new program and then extend what I'm doing, in the field automatically or automagically, if you will, right? So and then it kind of opens it up.
Right. So right now, how those devices or solution works, because you said like there's this red company thing, right? And you mentioned that it seems that they have an API, but then you can have option to talk over serial. Then was another option that you have just a browser that you cannot do anything with it. So what are those guys normally doing? Like, let's say I go to a company that produces, I don't know, some refinery or something like that, right?
Let's walk through it like in real time what the actual user does or the engineer does to have this sort of thing. They have their Windows computer. It actually has a custom program. It actually has a couple of different custom programs. One for the SCADA stuff, one for the HMI stuff, which is usually totally different from the SCADA, right?
Okay.
You have like a SCADA system and you have an HMI system to actually to operate the distributed control system, the DCS. And the DCS, which is a completely different system. So we have 3 side-by-side systems. A lot of them do some of the same stuff. They just don't have the same things going on, right? So could I do data acquisition with the DCS? Yeah, you probably could. But then, that's not the way the DCS are programmed because they wanted you to use this other SCADA thing. So calling out manufacturers again, I've got my Wonderware over here. I've got my RS5000 control logics, my Rockwell workstation that, updates the PLCs right here. And then I've got my special HMI over here, which, may not be a web-based HMI. Most likely it's a custom executable running on a Windows machine that I then program from the Control Logics platform. And then I send it over and say, hey, this is the HMI I want to build too. Here's the code for the HMI. This is what's going on my PLCs, and this is what I want to represent. There's a tank. There's the 2 valves to the tank. There's a pressure level sensor and things like that. And I program all that into my HMI so someone can see the water rising and falling and, inside the thing, if this valve's open or this valve's open and that sort of stuff. And that comes directly from the engineering workstation. It floats into that custom executable in the HMI. You'll notice none of this is load balanced, right? None of this is resilient. If I kill that HMI, I might not have another HMI. If I have to go patch that thing it's down. The process is down. My engineers cannot see what's going on in that process while that's being patched or rebooted, right?
A quick question.
Then I've got,
Wait, because there's too many things going on, and I'm just trying
well,
to.
that's the problem. That's the other problem with this whole stuff is there's too many things going on, too many stacks of software.
Right now,
Right.
are you talking about three separate devices that talk between each other, or one device with three different pieces of software?
3 different devices, 3 different pieces of software.
Okay.
Only 1 or 2 ever talk to each other for special functions.
Okay, so there is one device that is pulling data from the sensors, and another
That's
device that is displaying that data, correct?
That's correct.
Okay, so the device that is getting this information passes it on to the other one that is displaying, but in a non-standard way, and probably just binary data in just super custom protocol that nobody can access, or maybe if you have to know how to do it.
The HMI does the because it's got to be real time, super duper real time. So you have to custom write your own executable. The other thing that's grabbing the data that passes it on to other systems that do loads and stores, like historians and ERP systems, to know what's going on with your facility, and that uses a protocol that's well known called OPC. And the current terminology for OPC is Open Platform Connect. But Matthew, what was the original term for it?
No, OPC. It was originally called OLE, Object Linking and Embedding, for process control. So again, we're going.
David, do you remember what object and linking and embedding is all about? Do you remember that? It's very Windows-specific technology.
I'm showing my age here, but back in 1994, 1995, there was this little project that Microsoft was running called Chicago, and Chicago became Windows 95. Microsoft was also pushing Windows NT 3.5 as a platform to replace proprietary Unix systems or other legacy operating systems. Anyway, without going into the big history lesson here, right? Microsoft had this really interesting technology called OLE, Object Linking and Embedding. And object linking and embedding, all right, basically sat above something that was more lower level, which was called COM-DCOM, right? The component object model, or the distributed component object model, DCOM. There was also another old technology which is called DDE, Direct Data Exchange. And a lot of SCADA systems today, a lot of process control and automation still use DDE, COM and DCOM and OLE. And when we talk about OPC today, and we talk about OPC DA, right, which is the original OLE for process control, DA data access. This is a Windows-only protocol. Yes, there are some implementations, and they are very specific, very expensive, that have been ported across using some form of special license, special source code license for the underlying COM-DCOM code to implement in other embedded operating systems. So every now and then you do come up with some device or piece of machinery which doesn't run Windows but has COM-DCOM inside its special purpose operating system to allow you to run OPC-DA. But OPC-DA is like today is like that's dinosaur stuff, right? This is Middle Ages, right? The kind of things that were used during the Crusades. It's had its time. OPC-DA has been superseded by OPC-UA, which has got nothing to do with OPC-DA. OPC-UA is OPC, or like Objects for Process Control Unified Architecture. That's what the UA stands for. Mm-hmm. And UA, was something which was under, how can I say, development about 15 years ago, so late sort of like 2000, so 2007, 2008 was when I first heard about this OPC UA thing, right? And some of the work that we did were in the very early days of Field Cloud. And actually just before I left Schlumberger to join to create Field Cloud, right? I was working on projects where we were doing bleeding edge stuff with OPC UA because we thought that, hey, this is interesting. It's a way that we can run it inside a smaller Linux system. We can do it better in embedded, and it seemed like a good idea at the time. However, it's a freaking nightmare because a lot of the paradigm of the way in which you create a data taxonomy, which is a hierarchy of a namespace, is actually very rigid. And when you need to have some relationship within that hierarchy, you have to like traverse nodes in a hierarchy to basically deal with things that might be related to each other, and that's where it all falls over. And you end up hard coding stuff.
So that's what the majority of businesses or systems are using right now.
In big plants, I would say you still have a lot of OPC-DA because of the prevalence of certain SCADA or process control systems made by the big automation vendors, and the prevalence of data historian products, which are found in big oil and gas plants, big power stations, and literally these were kind of big, massive investments made. Very expensive.
And they only work with the original DA stuff.
Yes, and they only run on Windows.
Yeah,
as well.
I mean, it's scary to think those systems are running Windows.
Yeah, but here's the crazy thing: is Microsoft did an excellent marketing job on convincing enough players in the industry across the different sectors, and in particular automation vendors, that hold on, a change is coming. But and it's true, the previous technologies that we were using were getting stale. They were much more proprietary. They required, again, very proprietary hardware. So you couldn't basically take a generic, PC and load whatever you wanted on it. You'd ended up getting the full thing, right? So this is back in the day. So when I started in the electricity industry in the early 1990s, we didn't use Windows. In fact, it was rare to find a Windows system in the entire enterprise. We were still running MS-DOS on PCs for office productivity.
OS2 Warp.
Yeah. I'll get to that because that was later. OS2 Warp came later. I remember doing some evaluation of OS2 Warp and quickly.
What is that?
You never used OS2 or OS2 Warp?
No. I'm not that old.
Oh, ouch! Hey, careful! I still have all my hair.
Oh, okay.
Yeah. So no, OS2 was from IBM, right? And in fact,
that system. Wait, is that the same as IS400? No.
No. There's
It was their competitor to NT, specifically 3.5 that they were trying to push at the time. Remember that?
In fact, NT was a competitor to OS2 because Microsoft was involved in the development as a contractor to IBM to develop OS2. And OS2 was meant to be the successor for IBM DOS, which again Microsoft had licensed to IBM, and that's how Microsoft got their helping hand. So Microsoft...
Something is flickering my head.
And there was a dispute, and Microsoft really, and again, it all had to do with commercial terms and conditions and intellectual property and licensing, etc. And so Microsoft kind of parted ways with IBM. IBM ended up with OS2, and what Microsoft did, which was very shrewd, is they hired a guy called Dave Cutler. Have you ever heard the name Dave Cutler, James?
You're playing old tapes, yeah. I was thinking Alex as well.
That is such a...
We're not there yet.
That's the Texan term, playing old tapes, man. So yeah, we're playing old tapes now. But Dave Cutler was had been working at Digital Equipment Corporation, or DEC, or just digital. They kind of call themselves digital towards the end of their career. David, have you ever heard of Digital Equipment Corporation, or DEC?
No.
Okay, all right. So DEC had a very interesting range of mini computers, and
They created Ethernet, lest we forget, right? So, Radia Perlman originally worked there, and she even created Spanning Tree. So they're responsible for a lot of evils in the world.
yeah,
Matter of fact, most of modern processors are actually based on their alpha processor that they were years and miles ahead of everybody else at
oh
the
yeah,
time.
yeah. This was the very first 64-bit processor before Intel, and then Intel actually
Yeah,
brought the technology.
AMD and Intel owe most of their current architecture to the original Alpha. So most of them are very similar. The first one Intel created that was similar to Alpha was the Pro Intel 200. The Pro 200, was it? What do they call it? Because they had a very specific term for their processors, not the cores, but the previous to that one.
So there was Pentium, and then
the Pentium Pro, Pentium Pro 200.
So
that
there
was
the
it,
Pentium
right?
Pro, right? And Pentium 2, Pentium 3, right?
The first one that was super scalar, super out of order processor for them.
DEC ended up selling the Alpha technology, and Intel called it Itanium. So they differentiated between the 64-bit line that came from DEC, and they called that Itanium, and then the 32-bit line, which ultimately morphed into the 64-bit capable, which superseded the original Pentium. And in fact, the Pentium name still lingers around. But when they went from Pentium to their core systems and started adding 64-bit, they did their own thing. And that was their own architecture. But we're talking about much more recent stuff. I was literally playing a very old tape about Dave Cutler, who was the architect of a operating system called VMS. Okay? And VMS at the time ran on VAX hardware made by Digital Equipment Corporation.
And I will tell you, there are plenty of bottles plants out there in the world, plenty of fizzy drink water companies that still have VAX running their automation systems, running the thing that creates their bottles and blows the glass and operates the furnaces and everything, running on DECnet, which is the predecessor to Ethernet. So
1 second, guys. 1 second. Is this the UI that you're talking about?
Yeah, yes. That's recent, but that's recent. That was probably the most recent, because you mentioned Open VMS, right? So Open VMS superseded, and what Digital did, or DEC did at the time, is they basically layered on what was OSF, right, the Open Systems Foundation, graphical user interface called Motif, right? So that's kind of like, now we're talking about the pre-Motif days. Man, taking me down a trip, man. These are some old tapes, dude.
And a lot of that was actually like serial locations on that one screen that was behind the other one. So like there's a lot of the programming for this stuff was just all based on serial, and essentially it was like a big modem that would run in it. The serial cards would be like a big modem, a really nice modem, but nothing but a big modem that would actually essentially call up to each one of these pieces of gear to program them. So
absolutely. And so
there was the first version was in 78, right? So
yeah, that's absolutely right. That's absolutely right. Yeah. Man, this takes me back scary thoughts of working on.
In 2023, there is going to be improved cluster security update. So this thing is still being used and
and run out
not used, like it's being still worked on.
HP sells a specific line of machines that actually replace the VAX hardware when it goes bad. HP's got this whole line of Intel hardware that specifically replaces, so that everybody can still keep using VAX.
Yes, exactly. And Itanium as a processor architecture hasn't completely disappeared. HPE, we're still making Itanium-based systems.
If you want to get really special and everything, do you know your little GPU miners that you buy nowadays with your GPU card?
Yeah.
That's basically like an Itanium processor. It's very similar with the streaming SIMD instructions, all from a big, couple execution cores, and then you got these that's a GPU, and that's essentially the same architecture as the Itanium, almost exactly the same. So your GPU is the Itanium stuff.
Okay, interesting. Okay, let's go back to your stuff, guys. What you're
Sorry. We're off topic now, but there's a lot of history that goes into this, and that's the problem. Is that all this history is like a glacier, right?
Right.
And everyone only sees the tip of it, and they say, "Oh, you got to have this." Right? When all the rest of it, when you finally hit it or get anywhere near it, you run aground and your ship busts open and you see.
So, question to Matthew, right? So, because you're the hardware guy, so how is your hardware or going to be open and source and easy to work on?
Great question. That's awesome.
Well, yeah, no, it's a great question. I think we've, again, if we look at all the different, stages or generations of hardware that have got us to where we are today, right? Mm-hmm. There's been a pendulum swing from very proprietary, very specific, and even custom engineered versions of standard products that have gone into the factory floor or into the plant. Okay. Mm-hmm. Some of the old control systems I worked on in the beginning of my career were actually engineered by Digital's Special Projects Division in Maynard, Massachusetts, and were done on commission for big customers like Westinghouse, who were doing control systems. So you ended up with
they're all on little microcontrollers, which are about this big, and they ran at clock cycles like 200 hertz or 500 hertz.
Yeah, no, we're talking about entire rack mount shelves, and these were things with ferrite core memory in them. Okay. 70s vintage stuff. When I started,
core memory is like these little bitty circles that you have to see the copper coil wraps around it, right?
What? Those things? Holy crap!
Yeah, you could actually see each bit of memory, right, physically.
Wow.
Right? It's a little ferrite, iron core, right, with two wires in it. Anyway, I'm not going to get distracted on that. So the pendulum goes from there through to what we call COTS, common off-the-shelf systems, right? Uh-huh. So called commercial off-the-shelf systems, right, is the acronym. So COTS hardware, and we now into the PC era. Okay, and this was the one thing that Microsoft was very smart about.
And what year was this?
Started in the middle of the 1990s, right? It was when Microsoft were looking at how to best position Windows NT and Windows 95, particularly for industrial customers. And they were doing this in partnership with Intel, because Intel was very hungry to, again, secure high-profile, high-margin business in addition to consumer markets. So PCs weren't just for playing Doom. Mm-hmm. They were also for running crap like Wonderware or iFix in the wastewater plant, right? So, the same machine that you could run Doom on and have a cool game experience would also run your process control.
Mm-hmm. Okay.
And that era again went from total immaturity in the mid 1990s through to, again, kind of like past its prime. Mm-hmm. I'd say somewhere in the last 10 years, it was starting to move past its prime. Okay. Mm-hmm. And why was it moving past its prime? Was because of, number one, the move into the cloud for data centers. And number two, the rise of, again, these kind of more embedded and less PC-like hardware systems, like the Raspberry Pi, which we all know and love. Raspberry Pi created a whole new category of small single-board computer. Mm-hmm. And it actually democratized...
Inexpensive single board, because there's a ton of single board computers out there at the time, but they started like at $1,000 and were all custom built.
Yeah, exactly. And it wasn't actually the cost. And if, in fact, this is an important detail, is that yes, there's the cost of the actual hardware, but then there's also all of the support and lifecycle cost on managing the operating system, the software that gets layered into the actual product. Mm-hmm. In the embedded world, we talk about something called a BSP, a board support package. Now, board support package is normally a core set of code that allows an integrator or a hardware, a product, manufacturer to take a module or a single board computer and basically get an operating system running on it. Back
So there's
50,
Intel has put out their own packaging system. Have you ever heard of Yocto Linux before?
yeah,
Yocto, Yocto.
yes,
So if David wanted to go out and make David OS, you can pull up Yocto, and they've got something called BitBake, and they has all the BSPs that they support, board support packages, and that's basically all the hardware abstraction layer that you do on like Linux. It takes that board support package, which talks to all the firmware across all the chips on that motherboard, and it matches it up with what packages you want to do with a hardware abstraction layer. That sits on top. That creates your David OS, essentially. And then after that, you can, put your own applications on it or whatever, and your tool chains and, GUI if you want to, and things like that. And you package it all up, and you have a David OS distribution, right? Because adding all the extra pieces that would be specific to your firmware and your hardware abstraction layer, then you get all your software on top, and that's the full distro, not just the OS, right? And that's what Matt is talking about, is that BSP is pre-baked for you in Yocto. There's a couple of those also. That's one of the things that the Raspberry Pi Foundation did, is they created these BSP specific, so you didn't have to go out and create or find custom firmware or find the firmware everything to create a BSP for you. And that's the amount of technical debt, because everything Matt was talking about is all getting rid of technical debt for the user community.
Yep.
So if you can get rid of the technical debt and make sure you don't have to keep doing this stuff over and over again, you've just fixed a lot of problems. So go ahead, Matthew. Sorry.
Yeah, no, but I am absolutely, and you're absolutely right. And Yocto was also a game changer in, again, standardizing and making it somewhat more manageable. Although I disagree with some of the design philosophy behind, or the philosophy behind Yocto, because you end up building monolithic stuff. Okay.
Yeah.
And by the way, you end up with some of the other platforms that exist that are meant to help you do this, with things that end up being quite monolithic. And
that even happens with modern PLCs, actually, especially if they run Intel hardware in the PLC itself, which a lot of them do.
Yeah.
Even if it's a small microcontroller like one, or a small embedded processor in those PLCs, because they all have like small processors in them. It just depends on how fast the clocking runs on them and things like that. So you have those that also is very monolithic. So remember the whole thing we were talking about, taking containerization and flopping it out? All of a sudden you've made this monolithic design piece, which is the whole thing that I wouldn't say we're fighting against it. We're just trying to get beyond it because that's been great for a long period of time, but it's holding us back.
That's right. But it's also another thing about respecting separation of concerns as well, because what you don't want when you're creating this kind of monolithic sort of like target, image, right? That target image kind of like bundles, it's the kernel, it's basically shells and operating system bits, various daemons that need to run in the background processes, and then you may have some application software, and then you end up bundling this whole thing together. Anyway, that's the one thing I really disagree with Yocto. But back before we had Yocto and open embedded and those kind of multi-stakeholder initiatives, all right, each silicon vendor, and this was the bad old days of ARM, not the days we have today with ARM, but ARM would license, IP to a silicon manufacturer. They would take a set of blueprints from ARM, and they would make their own chips, and they'd do all sorts of funny things to give some proprietary secret sauce into their silicon. Okay. And yeah, some companies were making great system on chips, but some of them, if you want me to name names, I could name names, but there were some that ain't terrible. I could, because there's one that's just up the road from me, right, that actually got out of that whole market of system on chips that ran full operating systems.
There's a bunch. There's two main ones that is probably coming to Matthew's head right now, and not naming names, and they might be Hello Moto and my own home state, since I live in Texas.
Yep.
And they make instruments, or some of the bad guys whenever it came to that. And I don't say bad guys. I just say they had to create something specific for a market. They had to do it in a budget that made sense because they weren't doing these huge, massive runs. Not everybody was running out to the local store to buy their version of the processor, to put inside their PC. It just wasn't happening. So they didn't have the economies of scale. So sometimes you make these design decisions because the system isn't open.
Absolutely. Then you've got the company that's named after famous superhero comics. Okay. And those guys actually do make good silicon, but they added weird quirks and they did a terrible job of actually putting driver code into mainline Linux. And so what you ended up having to do is you ended up having to either use their kind of like custom kernel patches or code that was a complete, I don't know, nightmare to work with. And it was very much thanks to a bunch of French guys down the road, well, let's say down the road, 200 kilometers from where I live, called Free Electrons, okay, who put a lot of effort into actually taking bad code, refactoring it, and publishing it into mainline, getting the intention of Marvell saying, hey, guys, listen, this stuff really does need to be mainlined properly. Let's have some governance. And they managed to get it. And so that was a good thing. See, and I even mentioned the name of that, but everyone knows who famous superheroes are. But I had a great time with Marvell, with the first generation of Field Cloud products. Why? Because Marvell are very strong in storage.
Yeah. Very strong.
If you look at their chipsets for RAID
storage area card
and
for a long time.
Yeah. So back before we switched to NVMe for storage and we were using SATA, they were really 10 years ago the right guys to be working with. So of course, then you've got the that other company that's trying to buy VMware.
Which one?
The company that's just announced that they're going to try and buy VMware for like 60.
I posted an article on LinkedIn actually about it, and I was surprised there wasn't a lot more comments on it.
I'm not aware of it. I didn't know like VMware is going to be bought by someone.
Well, it's speculative. I would say that's still highly speculative. But that company also bought Brocade back in the day.
Yeah. And
Brocade actually had a very good software-defined networking platform that I was working with them and Fortinet before Fortinet had its own SD-WAN and local SDN, and we were working together on that. And all of a sudden, they said, "Yep, just a whole bunch of black SUVs, American SUVs, just pulled up in front. Things are changing quick." And all of a sudden, the next thing you know, they belonged to that other company, and they were buying it for some of those properties that. Yeah. The conflation of hyperconvergence and now hyper automation, which is the thing that Matthew and I are in. So hyperconvergence is a terminology that everybody knows very much because you're converging the OS and the hypervisor and everything else like that all into one storage blocks and things like that. And everything's actually on one system, but that system's then repeated in a virtual NUMA bus, if you're old enough to remember what NUMA bus, but almost like a virtual NUMA bus where I just have to have a stack of 3 or 4 servers, and then I have basically a data center for you, right? Yes. And because it's the storage area system and everything else, that's hyperconvergence, right? Hyperautomation is the thing that Matthew and I are working on, which is sort of like the next generation of automation, but in that perspective where you've got an open presentation layer. The special sauce that you want to do is actually your automation pieces that you do, like what you're designing for the end user. That's the thing you're delivering. The platform almost doesn't mean anything after that, right? It's open.
Let me go back to Matthew. So I ask you a question.
Yeah.
He is smarter than me, so it's a better choice.
So that's fine. Anyway, but the company that's about to buy VMware, right, is extremely well known because the processors or the system on chips that are used inside the Raspberry Pi, are made by this company. Right? That's number one. Number two, right, that company was highly involved in the origin story of the Raspberry Pi. In fact, if you look at the key engineers that design and still design the Pi today, right, they actually work for that company, and there's a relationship there. So it's not by, how can I say, it's not by accident, okay? The reason why we've ended up, and again, it's been very good for that particular manufacturer. But what he's telling is that they also bought Symantec and they bought Computer Associates.
Who?
The guys who are buying VMware.
No, but I mean, who is Symantec? Who's Computer Associates? Who are they? I'm just sorry.
Oh no, you're having a laugh. Yeah, no,
Yeah, yeah. I was just trying to have a joke with guys that have been in France for too long. So no, I'm just kidding.
Or like
in all seriousness,
old time enterprise IT people. But what is interesting is if we look at the portfolio and the amounts of revenue that's generated from services, including those portfolio companies, it's pretty interesting. But there was another piece which I think is perhaps not being spoken about, or maybe will be spoken about regarding this potential acquisition of VMware, is actually the sweet spot for the guys who want to buy VMware is on smart NICs, so smart network interface cards, or they're known as smart NICs, but they're a lot more, right? It's very much about pushing more intelligence down into that interface for the network.
So it allows, that's the new thing, right? So they oh man, as well as compute cards, like different
exactly. So these compute cards. So it's very much the kind of thing that we have in mind with evolving the hardware design of the gateways that we do is about building these cards that basically go into a chassis, so it's more modular. And there's a couple of interesting, I would say, bleeding edge things. I'm not sure if you've come across a company called Turing Pi. Have you come across Turing Pi?
I've dealt with Turing before, yes. Yeah, okay. But not Turing Pi.
Now, Turing Pi, right? These are the guys who make a Raspberry Pi cluster.
Yeah. Oh, yeah. I've seen those. The 3 cluster nodes. Yes. Yeah. They have the switch.
So you got a motherboard, right? And then you got these slots. And they originally did this for the Raspberry Pi Compute Module 3, which was in SODIMM format. Yeah, there you go. That's them. Yeah, that's a Turing Pi 2. Okay.
And that's a switch ASIC, not a NIC. It's a switch ASIC that's actually built directly into it.
Yes,
which is different.
It is. But the idea with this is that you could then also add in NVIDIA Jetson boards as well. And so you can basically mix and match and do some pretty funky stuff. It's an interesting... I think they've got...
Matthew, I got made fun of by Ron Brash, who you may or may not know. He's now with Aeolus, formerly with Verb Industrial. And Ron's been around. Ron's designed PLCs for manufacturers that I'm not allowed to mention,
sure.
The NDA and stuff like that. But once upon a time, I was with a cybersecurity company that I worked for a very long time. And at the very beginning of the cloud revolution, one of the things we were trying to do internally as part of a Skunkworks project was to say, hey, can we get our ASIC that we custom build for our security gateways and the TCP acceleration and even traffic offload, like set up and tear down of SSL connections to be able to scale, 100x or 10x, the amount of TCP SSL connections that you do, for these sorts of, these sorts of transits. Just if we did the SSL inception alone, right? That would be super duper scalable, and we could just sell the card on that alone if we took our card. The biggest problem we had is a lot of the design of the chip is built directly into the firmware itself. So you have a firmware blob that loads dynamically. How do you protect that firmware blob? Because the easiest way to reverse engineer a chip is through the firmware blob that you get.
Yeah.
Right? And that is where creating a software mezzanine, like a T2 chip would be for passwords, in the Apple Gear. And I think the Pixel has its own M1 or something like that, where they do, passwords and, data that's almost like its own smart card with its own little bitty bus that, has operating system hooks. You would actually, to make this stuff, to make board manufacturers really take to it, so not everybody was, reverse manufacturing their chips, the firmware blobs would have to have somewhere to go that would interact with and be like a secure mezzanine where, once they dynamically load, to start loading your driver and things like that, because it's a firmware driver, right? Firmware reaches out, has to load some of the firmware into memory. That's that firmware blob I was talking about. Your driver interacts with that and, hooks up to the kernel, of the operating system. You have to be able to protect that blob. And so nobody's going to sell a damn card in the entire world where they can't protect their firmware blob to some degree. So you almost have to have virtual software mezzanine, like a T2 chip that would actually keep this stuff, super duper secure. Otherwise, I can reverse engineer every card ever stuck into it. And some people, they don't have a problem with that.
Right.
But that's the reason why you have, OEM drivers in Linux, and then you have open drivers in Linux, right? But the open drivers have taken forever and ever to evolve because they are having to basically reverse engineer not just the blob, but also how it reacts and everything. That's not really an open system at that point, right? Because you have all the special sauce that's not being used appropriately. If we would fix that problem, hell, if you just go to Linux Foundation and find out what they want, find out what Linus would want to see, you would fix all this in an instant. But somebody has to go create that hardware, and it has to be open.
Yeah, absolutely. But this is really where it gets it's quite an interesting challenge. I again, James, I'm not sure, and David, I'm not sure, well, if you were aware of this, but earlier this year, so around February, there was Intel had actually published or had done a pull request into the Linux mainline kernel to push something which they call the software-defined silicon driver, or the SDSI driver.
This is the beginning of it. Yep.
There we are. And this is the very beginning of what you just spoke about, right? So it's there. And in fact, the code's in the kernel. It's just that there's no silicon on the market that actually does the underlying magical bits and hardware. But the whole idea is that, yes, this is a way of having... It's coming.
Go check the hardware specs on the Pluton processor from Microsoft. And I think AMD was the first one to initiate it. It wasn't even Intel. So go check that out, because I do believe they actually have a way to encrypt specific SRAM to where you can now keep firmware blobs for that SDS on it. Nobody's developed for it yet. I don't think the SDS is ready. It's not ready for prime time, but we're getting close to that request.
Yeah,
it's getting there.
Yeah. And
I asked for that until 6 years ago. So someone's late. So
yes.
So Matthew, going back to the question about how is your hardware going to be open source and stand the test of time?
So I think we're going to come back to the good old definition of what a true open system is, or an open platform, or an open, let's say, an open system. I like that word, or I like that term better, right? Because there is always going to be a mixture of things that are closed and open, right? For various reasons. Okay, are we going to again expect, for example, this on the silicon design, right? That all of our silicon is open source, published designs, right? Can you actually, get the underlying design document that allows you to tweak that? So there is some interesting movement there in the hardware space with OpenRISC. So I think OpenRISC is moving into an interesting space there. It will be interesting to see how that, again, might influence the direction of travel for the entire ARM ecosystem.
Yeah, because the whole point of that processor was like, if you do something custom for someone or for yourself, you can always figure out how to update it, make it better, or change the hardware itself, right?
Well, yeah, and it also allows that the actual silicon design to be remixable, right? So you could take,
the first thing Matthew did was to keep his hardware open. It was he actually decoupled the processing power from digital I/O.
Yeah,
and that is already doing that alone has already revolutionized some of the stuff that we're doing in the field as part of automation and democratization of this sort of thing. So decoupling DIO from the compute, the programmable logic that does the compute that does the logic itself is already the first step, right? But it's got to be baby steps, and we're waiting for some of these other dominoes to fall, because even my own system, without containers, there was so much other technical debt that had to be getting through for us as a full ecosystem. We had to get through that technical debt, containers, API layers, using an API layer to do application deployment on, as opposed to some sort of kernel level type stuff like Win62, Win60, or Win64, Win32, or Linux Linode type stuff. So those are the things that the technical debt had to be as a whole ecosystem. So just now these things are starting to emerge. That's the great thing about vlogs like this, is that we start talking about how this stuff is emerging, give you a basis in history, where it's going to, and where we hope the whole system lands up. Unfortunately, it's always everything's a compromise. So who knows where it's going to land. This is the pie in the sky. Some of it.
Yeah.
The opposite end will probably get us somewhere in the middle, and there'll be compromise.
So you guys, you want to make a hardware solution where you have your custom board that is tailored to whatever problem that needs to be, like so reading sensor, managing valves and whatever, and then use, for example, the compute module of the Raspberry Pi to just slap it in, load the software that is open source that you can play with, and then if something goes bad with the Raspberry Pi, it's easy to just buy another one for $30, put it in, and re-roll the software, right?
There you are. And what really gets interesting is that now that we're seeing yet a new category emerge, which is this form factor. Actually, it's not a category; it's a form factor, right? With the Compute Module 4, is that there are other hardware manufacturers that are bringing out pin-compatible design of their own module. So you could get a Rock Pi or a Banana Pi instead of a Raspberry Pi Compute Module 4 compatible module. So that gets really interesting, because it means then that I could take the same carrier board, the same baseboard that we've got, right? And I can substitute a CM4 with a Rock Pi if I wanted to. And that could be very interesting. It also means then that we could then consider taking the form factor and actually engineering a specific CPU module with its own memory, which for me is also really exciting.
Which is what Pine is trying to do as well, right? So there's a couple of those companies that are trying to start kind of democratizing their designs. I just got hit up though, gentlemen. I'm going to have to go ahead and exit.
Okay.
I really enjoyed this talk. Matthew, I think the first time you and I talked, across the wire, I think we had like a 2 or 3 hour talk.
Yeah.
This doesn't stop that. Hope to be invited back again at some point in time soon, because we love to nerd out on the old history of everything else. And of course, two old guys.
This was a great conversation, James. Honestly,
we didn't even mention the Amigas yet. So, I mean, we haven't even gone into that yet, but maybe we save that for next time. So don't you dare show me anything.
I don't have my vintage computing stuff is around the corner. I do have some vintage music equipment though. Do you know what this is?
Oh, Roland, man, I cannot believe you have that old machine, dude. Awesome.
This traveled all the way from South Africa to France.
The DACs and those were like impossible to beat at the time, and they were so expensive. So that piece of hardware you see him holding in his hand was ridiculously expensive at the time. So, So,
19.
Well, gentlemen,
all right.
Cheers. It's been an absolute pleasure. Again, bye, y'all.
Cheers, James. Take care.
All right, so if you want, we can still talk about the hardware stuff, because you were mentioning something about the CPU, Raspberry Pi CPU open something, and not sure I was following that. Yeah,
so anyway, the thing is it's really not that important that the silicon, so the processor or the system on chip has proprietary bits in it, right? Mm-hmm. That again, the actual hardware design of the Compute Module 4 is proprietary to Raspberry Pi. That's okay, right? But the fact that we've got a standardized interface and the correct abstractions at that level is brilliant, because it allows then anyone, including my company, to engineer a board, right, that has peripherals on it that is fit for purpose. So the difference, and coming back to that big pendulum swing of proprietary hardware to COTS to the PC era, is PC was one size fits all. It's basically saying, hey, you buy a PC is a PC, right? We all know that a PC wasn't really a PC, because you did also have some standards for, peripheral cards, so
Right.
PCI bus, PCI Express bus. So buses were standardized, and we're taking advantage of that standardization and that openness that entered into the PC era. It's just that, again, what it ended up doing is it ended up swinging again into making very specific hardware. If you think about laptops today, right? Laptops may have the same buses inside for peripherals, but the peripherals are actually engineered into the same circuit board so that they take up less space and that it doesn't
Right.
get so hot, and it's smaller. It fits
Right.
in your lap, right? So the same thing works with smartphones, and the same thing now works for various devices or equipment that goes into factories. Okay.
So the question then comes like, so for example, you have your device in a factory, right? And let's say the module fails for whatever reason. Do you think the people in that company are would be confident, or they have the knowledge to know what to do to replace it?
It's not so much that they need to know how to replace it. It's about making sure that the product is maintainable over its life cycle. So, normally what we would do. So again, it all depends on what.
Yeah. So how do you teach them, or like how do you have like do you give them also documentation that explain exactly how this device works, and if we guys die in 20, 50 years, someone still will be able to figure it out how it works?
Not really. I mean, that's kind of a bit of an old way of doing it. But again, it depends on, are we building something which is 100% custom or dedicated for one customer, and that customer takes over the responsibility? Then of course we'll document it, we'll provide, and we'll train, and we'll spend time so that things are up and running. If it's a product and we're providing a solution and we're part of its life cycle, then we're involved in maintaining it.
Oh, okay. I see.
Okay, we're involved in maintaining it. We're involved in servicing the equipment. We're involved in swapping out hardware if it breaks, and making sure that there's spare parts. And that, to me, is important, So it's the same way that, like, for automobiles, I mean, how involved is your car, manufacturer, all the parts manufacturers in the supply chain? How much are they involved in servicing your vehicle, right?
Right, but my question, okay, so that makes sense. But let's say that you decide, like, so let's say like you're a successful business and everything is great, right? But as we spoke with James, he was talking about solutions that are like 50 years old, even older, that nobody knows anymore how it works, but they still work, so nobody's touching them, right? So how are you guys going to prevent that situation? Like,
So
50 years from now, you die, the company doesn't work anymore, and all of that, right? Then this business is left with legacy hardware that nobody knows how to use.
it's a great question, because part of the challenge here, and this is where I think a lot of value can be added, and it's not about the technology, it's not about the project even. It's about actually the understanding and the shift in understanding that automation equipment, control systems, data for the enterprise that comes from the factory floor, that there is a different life cycle involved, and that, again, the new way that we work involves a continuous refresh of hardware. Okay, and it doesn't matter, right? It's not traumatic. This is really hard to do, though, because many decision makers in large industrial companies, large industrial enterprises who do manufacturing, still think that it's part of their actual manufacturing asset. So when I am creating a new production line or a new boiler or a new unit in a factory,
Mm-hmm.
or if I've got a unit and that unit's been running for 40 years, okay.
Mm-hmm.
So part of the reason is part of the way we have that conversation is by looking at, for example, very big units or an entire factory. Hey, you guys are in the same building that was built 120 years ago.
Mm-hmm.
Seriously, David, all you need to go is go take a look at some of the ecosystem around Turin, Torino,
Right.
and look at Fiat's home base, and
Yeah.
you look at some of the buildings, and then some of the tools and some of the machinery that has, and some of it has lasted for a very long time. It's actually great
Mm-hmm.
value for money. If you look at
Right.
it, those assets were depreciated decades ago, but they're still good.
Mm-hmm.
So okay, so what are the things that you add or change around those things that last for a very long time, and appreciating that some things are going to last for a short while, but it's the total system that is actually going to be almost have infinite lifespan. Right? If I'm producing something that the world needs, let's say take water for example,
Mm-hmm.
or let's take or I'll use water as a first example, and we'll talk about energy. So
Okay.
water is kind of easy because water is water. It's H2O.
Mm-hmm.
We know that we will use clean water for consumption, and we know that we will basically have wastewater that will need to come out of whatever we're doing. Right? This is a
Mm-hmm.
basic.
Right.
Okay, the ability to produce clean water and the ability to take wastewater and turn it back into, let's say, water that is fit for the environment
Mm-hmm.
or fit for consumption. All right, that those requirements, right, haven't changed for
Right.
hundreds of years. Okay, but the techniques, the technologies, the processes, right, are always, how can I say,
Evolving, changing, improving, getting better, faster,
they
cheaper.
exactly. And this is going to always, go
So you're
through.
saying that those companies should think about this type of embedded systems as something that they have to change over time because the processes that they're doing must change anyway. So the board that you design to
But
read sensors and
yes,
whatever, they
but
have to be updated because the new sensor now it's instead of 12 volts runs on 5 volts, blah blah blah.
but again, all of that should not be traumatic. There shouldn't,
Right.
again, there should be no fear about this, because what tends to happen is that there's fear. We're 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 how can we say, we've got all these risks. It's like what if,
Right. But
right?
so if you guys have this standardized software layer that runs into the system, right? And so let's say I'm a company like this Purify Water. I ask my internal team to develop a fancy dashboard, some automation with like alarms, whatever, by acquiring all this data.
Right.
They should not be fear that, okay, if we change the board that talks with the hardware, anything is going to, we have to rewrite everything, right? Because the software
Exactly,
is going to be the same.
exactly. Because look,
And the hardware is basically almost meaningless at this point, as long as the hardware talks to your software layer the right way.
yes, and remember, it's all about good abstractions.
Mm-hmm.
It all comes down to, okay, good abstractions in hardware, abstractions in software, abstractions in again, data and
Mm-hmm.
formats as well.
Right.
So again, with the right kind of abstractions in your overall architecture,
Mm-hmm.
you're going to be able to again replace or duplicate,
Mm-hmm.
all right, functions in a
Mm-hmm.
way that does not cause trauma. So the whole thing is, it's like, no, it's a zero trauma architecture.
Right.
So if, for
Okay,
example,
that's
yeah, it's a
no.
zero
I'm,
trauma
I'm saying like
architecture.
this is now understanding like this is actually pretty cool. And so my last question would be: do you guys right now have a website where people can find this or more information about this, or right now you have two separate companies and you're like collaborating together?
So I mean, we're still very much arm's length. James got his thing in Houston. I've got my thing here in France. At some point, it's going to make sense for us to actually go out and do something for either the same customer or through the same value chain, which I think would be exciting. And we're exploring how that might look. I think that's good. And I think, because a lot of this is very new, we need to build more content, which is part of the reason why we're having this conversation. So we could, again, share our thoughts and gauge interest, and then basically start summarizing this so that we could, again, communicate better. But I think what I like about what we've just been discussing for the last hour and a half is, yes, so ultimately this is about a zero trauma system, right? Where, again, my sensor so again, a sensor, right? Again, parts within my machinery, a sensor, an actuator, a connector, right? Those things are going to, again, replace, wear out, okay?
Yeah.
So I've got something that's on a motor, and it's a moving, rotating part, and it's going to have wear and tear. Right. And so from time to time, you will need to stop and replace it. So imagine if you were able to, again, limit the amount of stops you had to do to replace certain components within the system. Or the fact that, again, changing automation or changing your data systems that are in the heart of your automation and process control, that this is again as simple as swapping out a component. And actually, you're not even swapping out a component, because all you're doing is you're duplicating and then you're taking something away. Imagine, again, in machinery, it's a little bit difficult, right? It's actually very difficult sometimes to engineer a mechanical system. So you've got redundancy and duplication in the system, so that, again, if one component fails and I have another component that is actually working, and again, I can change the broken component without stopping my whole system. That can
so you have like a redundancy built in.
Yeah, so it's about being redundant. Yeah.
Right. So I mean, you could. So that's why James was talking about the load balancer, because you could have two Raspberry Pis running, and if one fails, it can switch to the other, and vice versa.
Well, you could. That's still looking at the Raspberry Pi as a complete thing with its own, again, with also with a classic operating system view of the Raspberry Pi. But also load balancing is used inside, because you've got duplicated containers that are running inside the Pi.
Oh, okay.
Right. So if you take
when you want to switch a new version to a new version, the load balancer will just the one that talk to this new container, because this is the old one, right?
Exactly. So if I've got a software component that fails, or again needs to be upgraded, I have that flexibility where I can deploy in, or I can duplicate, right? And then have redundancy in the system, and then spread that across multiple hardware nodes. This is the powerful thing. But again, we're literally taking all of the underlying beauty of the cloud, and we're bringing
it local.
The cloud into the factory, right?
Yeah, so I mean, I like this idea.
Because
I also think like the whole cloud design approach, it works very well in operating systems and also embedded devices.
Yes.
Because on one board you can condense all the best parts of how the cloud was designed. And because, for example, the thing that I'm missing from operating systems is the triggering system that exists in AWS, for example.
Yeah.
So where, like, instead of checking if, is this file created, is there data, right? You get the operating system tells you like, hey, there's new data, do something with it if you want it or not, right? And I like that reverse thing, that your application just sitting there and just registers someone, and the OS tells you when you should do something about it. And that's a cool design that I enjoy very much in the cloud, and I wish the operating systems had like this thing built in by default.
Yeah, no, definitely, I agree. And if you think about it, I mean, your workloads that run, for example, in AWS, I mean, is there a workload actually running all the time over its life cycle on exactly the same physical hardware?
No.
Definitely not.
Right.
The unfortunate thing is that you and I don't know anything about that underlying infrastructure
Hmm.
because we're not on the inside of Amazon or not on the inside
Right.
of AWS. And so again, many developers or many, again, folks involved in IT today, they take that wonderful redundancy and wonderful resiliency for granted.
Hmm.
Because, hey, my cloud vendor is doing all the magic behind the scenes.
Right.
Um, Again, this is very different in the process control world because the process control world, the customer is very intimately involved in defining the requirements and the specification and
Hmm.
ensuring that their supplier, the integrator or the controls vendor or the automation vendor, is actually meeting their specification.
Hmm.
Okay, so it's a lot more prescriptive and there's a lot more, I would say, sort of, again, awareness of some of the underlying technologies. But that being said, there's also a lot of black box
Hmm.
in automation. And so, again, the way the specifications are normally written, and this was also thanks to Microsoft back in the 90s and the whole
Right.
PC era that came out was like, yeah, but Windows, right? You don't need to think about what's inside Windows.
Hmm.
Don't worry, there's this cool thing called OLE and COM and DCOM, right? It's the magic thing that allows
Right.
us to do all this cool stuff. All you need to do is specify in your requirements that it's OPC-DA as your protocol, and all the rest is then happening anyway. That was
Yeah, and
Microsoft
then you
did
get
a fantastic
right.
job on it, right?
Yeah, then you get stuck, and 50 years later or 30 years later,
That's
you
right.
start to
That's
move
right.
from
That's right. That's right.
out from there.
And we see exactly the same thing with the major cloud vendors, with Google, Microsoft, and Amazon today, with the underlying cloud infrastructure. Like, hey, you don't even need to think about this because it just works, and
Hmm.
all cool stuff is built on top of it. Right? We'll take care of making sure that this workload that's running here is still going to run, even if the server gets old and we have to replace it.
Right. But I mean, this is again, we could go on a different topic tangent to talk about this. But I think this is a good way to stop today's episode because I think we were pretty on point on topic,
Yep.
thanks to James, which was nice. So, guys, thank you for watching and join us the next time where we're going to talk about something new and random.
Absolutely. Well, anyway, you're watching the second episode of season 0 of TMM, the Technological Mind Meld, with David Gatti and myself, Matthew Smith. So thank you very much for tuning in.
Thank you, guys.
Ciao.